Hello everyone, I'm Flor Vanessa Maciel, and today I'll be presenting on the influences of aerosols on ice and mixed phase clouds based on in-situ observations and CAN6 simulations. So first, a quick introduction. Ice and mixed phase clouds have a wide spreading spatial coverage over Earth's surface, and the radiative effects in the climate models often lead to large uncertainties in the total cloud radiative effects. Aerosol indirect effects, or AIE, on these clouds are difficult to quantify, partly because these clouds have different properties during their lifetime, and other factors such as thermodynamic and dynamic ones also play a major role. So, in this work, we developed two methods to quantify AIE on cirrus clouds and mixed phase clouds by categorizing different evolution or transition phases of the clouds based on aircraft observations. So let me go over the data methods for the Cirrus Cloud project. We used observational data from 7 NSF and 5 NASA flight campaigns. We compared observations with CESM CAM6 simulations co-located with aircraft flight tracks for each campaign and nudged with MERA to reanalysis data. And to better compare with model measurements, we calculated a course data set for the NSF campaigns, for which we used a running average of 430 seconds, which was equivalent to a horizontal grid space of 100 kilometers. In addition, we also excluded measurements at temperatures greater than -°C for our analysis. So let's go over these cirrus cloud evolution phases. We defined the 5 evolution phases for the 1 Hz observational dataset using the spatial ratios of ice supersaturated regions, or ISSRs, and ice cloud regions, or ICRs. These were found using relative humidity with respect to ice, RHI, and the ice crystal region, ice crystal number concentration, or NI. And you can see these spatial ratios in the table shown below. So let's go over these 5 evolution phases. Phase 1 is clear sky ISSRs. Phase 2 is nucleation. Phase 3 is early growth of ice crystals. Phase 4 is later growth of ice crystals. Phase 5 is sedimentation/sublimation. So some results. Here we show the linear regression between cirrus microphysical properties and aerosol number concentrations. We utilize delta values in order to minimize the impact of temperature and ice water content, or IWC, and then I show positive correlations with larger aerosols, so greater than 500 nanometers in the nucleation phase, or phase 2, and this implies the strong contributions of heterogeneous nucleation when ice crystals first start to nucleate. For the later growth phase, or phase 4, IWC and NI show similar correlations with small and larger aerosols, and this indicates that homogeneous and heterogeneous nucleation play similar roles in the later growth phase. Finally, we also found that the simulated AIE are weaker when compared to both the observation and coarse resolution observations. So let's go over the hemispheric differences in these linear regression comparisons of ICR phases and aerosols. So here we have the observations showing positive correlations between IWC, NI, and NA in the southern hemisphere compared with the northern hemisphere. And this implies a stronger aerosol indirect effect in this region. These simulations actually show negative correlations in the southern hemisphere. And IWC was actually underestimated by a factor of 3 to 30 in CAM6 for the early/later growth phases, again, phase 3 and phase 4. And this indicates that simulated IWC is biased to be lower, and thus ice particle growth is underestimated within the model. And this is consistent with the model biases of smaller vertical velocity variability and lower frequencies of ice supersaturation in the simulations. Let's switch gears and talk about the coexistence and transition from supercooled liquid water to ice crystals in mixed phase clouds. So for this study, we utilized data from the Socrates flight campaign, for which there are a total of 15 research flights. In addition, we restricted temperature from -40°C to 0°C. We also utilized a drive data set produced by the University of Washington with their ice liquid discriminator, with utilizes observations from the two-dimensional stereo, or 2DS probe, to categorize data into ice or liquid, and This data set uses cloud data from the Socrates Field campaign and covers all research flights except for research flight 15. So let's talk about these transition phases. So in this paper, we introduced a method that defines the transition of mixed phase cloud MPC regime into 4 phases, one being pure supercooled liquid water regions, SLWR, 2, SLWR with ice particles embedded inside, 3, partially overlapping SLWR and ICR, 4, pure ICR. And you can see these transition phases illustrated in the diagram to the right. In addition, the spatial ratios M1, M2, and M3 within the table on the lower right were found by calculating the ratio between the length of the cloud region, liquid, ice, or mixed, respectively, and the total horizontal length of the cloud segment. The spatial lengths were found using the amount of LWC and IWC in each second. So let's talk about some results. So the correlation between MPC, microphysical, and macrophysical properties. So here we define the ice spatial ratio, which was calculated by counting the number of seconds defined as ICR and MCR, then dividing them by the total length of the cloud segment. And this ratio is repeated for each second within that segment. The ice particle number fraction, or IPNF, was calculated by dividing the number of particles defined as ice by the total number of particles in the same second. For transition phase 2, both A and B have positive slope, indicating that the ice spatial ratio and the ice particle number fraction are correlated. And as this phase is characterized as when the ICR first starts to appear, there are no seconds defined as ICR. In the second column, the relationship between IPNF and ISR is shown for transition phase 3, which is characterized as when the ICR appears. Here you can see that the correlation between these variables is also positive. So let's talk about the correlation between aerosol concentrations and the ice spatial ratio in MPC. The relationship between aerosol number concentration greater than 500 nanometers is related to the cloud segment scale. In the first 2 columns, NA500 is plotted against the ice spatial ratio for transition phases 2 and 3. In A and C, there is a positive trend between aerosols and the ice spatial ratio. And this may indicate that NA500 might act as ice nucleating particles to facilitate ice formation for transition phase 2 when the mixed phase cloud region appears. Let's go over some conclusions and future work. So we just want to summarize for the Cirrus clouds that without separating these phases out, these cloud characteristics represent a mixture of all evolution phases which have large variations and different responses to aerosol. Here for the mixed phase cloud project, we just want to send the message home that this novel method allows us to consider the macrophysical properties of a cloud segment and relate them to the microphysical properties. It also allows us to individually analyze aerosol indirect effects on different transition phases from supercooled liquid water to ice crystals. And finally, we have some papers on these findings that go much more in depth than what I could cover here. So we would love for you to potentially read them. They are both in review currently. So thank you. And I'll be taking questions and comments now, I guess.